Hi everyone, this is Shivam. Welcome back to my channel. In this video, we'll be talking about how system design is done at a very high level, usually using AWS cloud components. This is a beginner-friendly video where we'll be covering topics like horizontal and vertical scaling, auto-scaling group, load balancer, EC2, database, read-write replicas, simple queuing service, simple notification service, FanOut architecture, CDN, CloudFront, caches. We'll be also discussing microservices architecture and much more, and how we can use this component to create a robust system. In this video, we'll be taking an example of Amazon.com and we'll try to understand how components work in real time. So without wasting any further time, let's go to the board and start designing the architecture. So let's take an example of Amazon.com. So as we all know, Amazon is an e-commerce website where traffic is massive and it operates at a global level. At a very high level, there are mostly two components, that is user and the server. So server is nothing but a physical machine which is capable of running 24/7, and it has a public IP address. So in this case, the public IP address is 100.2.3.4. In fact, our personal computer can also act as a server if we can assign it a public IP and if it is capable of running 24/7. So client can reach Amazon.com by hitting this IP. This IP is nothing but the address of the server. It is mostly like our home address, which has a street name, a street number, a state ID, a country code. But the problem here is that this IP address is very hard to remember, and this is where the domain name system, commonly known as DNS, comes into picture, which provides a human-friendly name which is easy to remember instead of IP address. So let's take a DNS server. So DNS server is nothing but a very big directory which holds which domain is assigned what IP address in forms of a key value pair. So whenever someone types Amazon.com, so the request goes to the DNS server. The DNS returns the IP of Amazon.com, and then the user is redirected to the servers. And once the request gets routed to the server, we get a response from the machine and we see the web page of Amazon.com. This entire process is called domain name resolution, commonly known as DNS. So as we all know, this machine has a public IP address and I have given it some physical resource, which is 2 CPU and 6 GB RAM. Now, when the traffic increases over time, there is a very high chance that this 2 CPU and 6 GB RAM will run out and our server will be overwhelmed with the requests. And when the server is overloaded, now we usually get this common error, which is out of memory error. So this is the reason when there is a sudden spike in the traffic, our server crashes and people are not able to see or access the website. Now that we have understood that server crashing is not a good thing, so let's make this server fault tolerant. So we have two options. Either we can scale it vertically and we can scale it horizontally. So let's discuss these two types of scaling in detail. So what happens in vertical scaling is that either we can increase the physical resources of this server from 2 CPU, so let's say 64 CPU, and from 6 GB RAM to 256 GB of RAM. This number might seem to be very big and is capable of handling much more traffic compared to the previous numbers, but there is a very high chance that when the traffic increases, this 64 CPU and 256 GB of RAM can run out of resources, and again we are stuck with the same issue where multiple people are trying to access the website and the website is not able to handle that much traffic, and eventually our website will crash, which is again a very bad thing for an e-commerce website. So what we should do as an architect or a system designer? So let's assume that money was not a problem and your system architect decided to take a very dumb step and increase the CPU to 8K and increase the RAM to 256 GB or 256K GB of RAM. So now this is a very powerful machine. This is almost like a supercomputer and is capable of handling much more traffic compared to the previous server configuration. Imagine this scenario that the entire world starts accessing your system at once, and this 8K CPU and 256K GB of RAM is capable of handling your traffic. But one important question to ask here is that whether you get this huge amount of traffic all the time, there is a very high chance that you might be getting very high traffic, probably 10 to 15% of the time of an year, probably during some festival season or during Prime Day sale. But during 80-85% of the year, the traffic is very low compared to the Prime Day sale. So what we as a company we are doing here is we are wasting the physical resources as well as the money. So what you did here as an architect, that you over optimized the resources, which is eventually leading to loss of revenue. So in vertical scaling, we are actually increasing the physical resources of the server. Like we saw earlier that we had 6 CPU and 64 GB of RAM. Then we increased to 64 CPU and 256 GB of RAM, and eventually we made our server into a supercomputer to handle all the global traffic at once. So here most of the cloud providers say that you as a company tell them that what's the optimal resources which is needed to run your website. And based on the traffic, whenever the traffic increases, they will add more resources. So this way company end up paying much less compared to running the server with 8K CPU and 256 KB of RAM. So till here, we understood what vertical scaling is. So vertical scaling is fine, but it has a very big problem that whenever the resource needs to be added or upgraded to the server, there will be a server reboot or a server restart, and there will be a downtime during the restart. You cannot add a resource or increase the physical resources of the server while the machine is running. So while the machine is rebooting, there will be a downtime and your website won't be accessible. Now just imagine this scenario that there is a Prime Day sale which has to start at 12 a.m. in the night, and by 11:50 p.m. the traffic is fairly less. The moment it is 12 a.m., there is a spike in traffic, and by 12:05, your server ran out of resources and there is a need to increase the resources. Just imagine the scenario that even if it takes 1 or 2 minutes for the new server to come up, can Amazon bear that downtime? The answer is no. Amazon needs to have a zero downtime so that it does not affect its customers. So it's clear that we cannot do vertical scaling here. So what's the solution here? So we all know that the traffic is increasing. So what option do we have here? Is there a way we can scale this server in parallel to the first one, which is 100.2.3.4? Yes, there is an option, and that option is called horizontal scaling. We can add another server with again same resources, and there will be a different IP address here. Let's say it has 100.2.3.5. Now, while the second machine is coming up, it will again take 1 or 2 minutes for the server to be fully up and running. So the first machine can handle traffic by the time second one is up and running. Now, suppose if the traffic further increases, we can spin up another machine. So by the time third machine is up and running, the other two machines are running and handling the traffic. What this means here is by the time the third machine is fully up and running, the website might be slow, but it won't be down as in case of vertical scaling. So this process is called horizontal scaling, where you add more servers instead of just adding more resources to one server. So one important thing to note here is that every machine has a different IP address. And we initially discussed that whenever a user hits amazon.com on their browser sends a request to DNS. Then the browser returns this IP address, which is 100.2.3.4, and the user's request gets redirected to the server. now that we have added so many new servers, so whenever a user is trying to access Amazon.com, this DNS is returning the same ID. So what this means is that even though we have added new servers, but all the requests are getting redirected to the same server instead of these new servers. So what's the solution here? Even though we added 2 new servers to handle the traffic, but all the new requests from the users are getting redirected to the same server. This is not what we want. So here comes another component which is called load balancer, and in case of Amazon it is called elastic load balancer. So what we do here is we add a load balancer in front of all the machines. So let me get rid of these users. So what is happening here is we added a load balancer in front of all these machines, and this load balancer will be having some IP. Let's say the IP address is 10.2.3.1. So what we should do actually, instead of registering the server's IP address into the DNS, the best practice is to register the IP address of the load balancer into the DNS. So what is happening here is that whenever someone tries to access Amazon.com, the request goes to DNS. The DNS sends the IP address of Amazon.com's load balancer, which is this one. The request comes to user's browser. Then instead of getting redirected directly to this server, the request gets redirected to the load balancer. And now it's the job of the load balancer to distribute the traffic among these available servers. So with time, when the load increases, so all the users are getting redirected to the load balancer. So with time, when the traffic increases, we can add another server here with a different IP address, let's say 7. Again, when the load increases, the load balancer will send request to the new server. So what is happening inside this load balancer, or in case of Amazon, it is called ELB, it is called Elastic Load Balancer. So what is happening here? So there are multiple algorithms which are configured inside the load balancer, and the most commonly used is the round robin. So what this means is that the first request will go to the first machine, the second request will go to the second machine, the third request will go to the third machine, the fourth request will go to the fourth machine, the fifth request will again go to the first machine, and so on and so forth. Now, if we spin up another server, then load will be distributed accordingly. Now, load balancer knows that there are a total of 5 servers which are running for Amazon.com, and the loads gets distributed evenly on all the services. Now the question here comes is that how load balancer knows that there is a new server which is coming up and how to send traffic to it. So whenever a new server is spun up due to increase in traffic, then you need to register this server with the load balancer. Now this is how load balancer knows that, okay, there is a new server which has come up and load balancer needs to send traffic to that new server also. Now suppose with time the load got decreased and we don't require this 5th server. So we can delete this server, and the load balancer knows that the server has been deregistered from the load balancer. Now this entire concept of scaling is known as horizontal scaling. So one important thing to note here is that load balancer does not just start sending traffic to the new server the moment it is up and running. So as we discussed earlier, that it takes at least a minute or 2 for server to come up and start running. So before sending traffic, the load balancer does a health check on the server and sees whether the server is healthy for at least 1 minute. Only if the server is healthy for at least a minute or so, then only the load balancer will start sending traffic to the new server. If the server is not healthy, the load balancer will not send traffic to the new server. So now the question here is, how does server knows that, I have to spin a server? What's the parameter which decides that I should spin another server while the first one is running? So at a very high level, I'll say that there are some policies which are defined which continuously monitors the server's resource. So suppose we have the first server which has 6 CPU and 64 GB of RAM. So we can set a policy of this server resources. For example, when the CPU goes above 75% and when the RAM goes above 80%, start spinning a new server, which means that we are reaching the 80% limit of our first server and there is a high chance that we might run out of physical resources on first server. So by the time 90% of the resources of the first server is consumed, the second server is up and running, and hence we prevent server from getting crashed. So this concept is known as auto scaling, and in Amazon it is done via auto scaling group. So that's a different topic altogether, which we will discuss in some other video. But for now, just understand that there is a policy which is continuously monitoring the resources of the server, and the moment it hits the threshold of that policy or threshold of the resources defined in that policy, the auto scaling group will automatically spin up a new server to prevent your previous server from crashing. Now you might think that this load balancer is also a server, and what if this gets crashed? So in reality, this load balancer is being managed by the cloud provider, and this load balancer has enough resources to handle your traffic so that it works efficiently without getting crashed. Let's now discuss the microservice architecture. So in microservice, there are multiple services like API service, auth service, orders, and payments. So let me create services here. So now that I have created all the services, let's look into these services. So auth service is responsible for authenticating the user. Again, payment services is managing the payments, and the API services are managing the API calls here. We can also see that there are multiple number of servers. By the way, these orange blocks are called EC2. So in AWS terminologies, these servers are called EC2 servers, which gets scaled horizontally automatically based on the load. One important thing to note here is that auth service has more number of servers compared to order services or payment services. And what's the reason behind this? Auth service has more number of servers because everyone is trying to browse the items on Amazon, but not everyone is actually buying those items. Hence, the number of servers or payment services or order services is less compared to auth service. Now, what if someone tries to access auth services via URL? Let's say whenever someone types /auth. So whenever someone types this URL amazon.com/auth, the request should be redirected to auth services. Or when someone tries to access order, then the requests should be redirected to order service, and similarly for payments. In order to achieve these routing logic, we need some kind of server which can route these URLs based on the request. We need something like a routing logic server, and in case of Amazon, it is called API gateway. So let's put API gateway here for routing logic. Let me adjust these first. API gateway is responsible for redirecting the request based on the path. So suppose if someone goes for order, then API gateway will redirect this entire path to order services. Now here is another issue. Suppose we define the route which has to be routed to specific server. But when the request gets routed, suppose to auth service, then how the routes will know that out of these 8 servers, which server to pick to complete the request? So technically we'll be needing a load balancer in front of these 8 servers for auth service. As we have discussed earlier here that Amazon has Elastic Load Balancer which distributes traffic evenly across multiple servers. So we'll be needing a similar kind of setup here in front of each services. So here we'll be needing a load balancer in front of order services, another load balancer for auth services, one more load balancer for API services, and one more load balancer for payment services. Now that I've added a load balancer in front of each services, Similarly, we can create a logic in the API gateway so that whenever someone tries to access auth, order, payment, or the root URL, the API gateway will forward the request to its respective load balancer, and the load balancer will forward the request to the respective server of that service. Now, the next thing to note here is that since we have created a microservice architecture for our system, and we have also defined routes for different services. So whenever someone hits amazon.com, the request from the DNS should come to this API gateway, and this API gateway is responsible for sending the traffic to the respective services based on the URL. So suppose someone tries to access amazon.com, then the request should come to API gateway first, and then API gateway will forward the request to API service. So let's try to configure that. Suppose this API gateway has a IP address of 1.2.3.4. Now what we have to do here is we have to configure the same IP address on the DNS so that whenever someone tries to access amazon.com, the DNS will return the IP address of this API gateway, and the user's request will get redirected to this API gateway. And then based on the route, API gateway can forward the traffic to respective services. Now that we have designed a robust microservice system here, there must be some batch processing which is happening in the background. So what it means here, suppose someone uploads an Excel sheet with the names of all the Prime customer, and they want to trigger an email saying that, hey, there is a Prime Day sale on so and so date. Now imagine this scenario. There could be millions and millions of people who are Prime customer, and is it possible to run a loop to send all the emails to Prime customer? Well, technically it is possible, but that will not be a very efficient process, and it will also consume a lot of physical resources like CPU, memory. We can also think of this scenario as whenever someone places an order on amazon.com, as soon as the payment is successful, the customer gets an email confirming that your order has been placed, there is a delivery date, and it also has some other information regarding the order. So what is happening here, that the payment services, this payment services is trying to trigger an email whenever there is a successful payment. Now this email server is actually communicating with an external email client or API, which is actually sending the email to the customer. So let me take here. So there is an external client. So this email server is trying to communicate with this external client to send an email. And when this client successfully sends an email, it sends back a response to email server, and email server sends back a response to payment gateway. Now imagine this. So we discussed that whenever there is a successful payment, the payment services is triggering an event for email server, and email server is trying to communicate with an external email client, which is sending an email to the customer. But imagine this scenario, that within a second there are 1,000 or even more number of customers who are placing order on amazon.com. So whether this single email server or this entire infrastructure of payment, email server and email client, will it be able to handle thousands and thousands of email in a second? There is a very high chance that many of the response from the external client or API could get lost, which we do not want. So what's the solution here? Now here comes another service from API, which is called Simple Queue Service. It's a queuing service which works on first in, first out algorithm. So let's create a queue service. So now what will happen, since we have added a queue system which is SQS in the middle of payment service and email server. So what will happen, that whenever there is a successful payment, the payment service will create an event and it will put that event into this queue. So there could be multiple events which are being placed by payment service into this queue. Now what email worker will do, that it will pull one event from this queue and it will trigger an email, and once the email has been sent, this event is discarded. Similarly, it will pick another event from the queue, send email, and then it will discard the event. So let me put arrows for it. So this will pull event. It will not, the queue will not push event, but instead the email server will pull event from it, send an email, and then discard the event. So that's the reason you must have noticed that whenever you place an order on amazon.com, you get an email after, let's say, 5 seconds. So This is the architecture behind it, that whenever the payment is successful, the payment service puts an event in the queue, the email server takes that event, triggers an email, and then discards the event. So this takes around 2 to 3 seconds for email to get triggered and to be sent to the customer. Now what we can do here, in order to reduce the processing time of this email server, we can scale this email server horizontally. Let's add 3 servers here. So what it will do, that it will start processing 3 events in parallel, and this will reduce the processing time of email which is being sent to the customer. So once the email is sent, the email server will send back the response to payment services that, hey, the email has been triggered and sent to the customer. Now, one important thing to note here is that this entire thing where the payment service generates an event and the event gets pushed into the queue, the email server picks it up and sends an email, and then the payment services gets a response. So these entire thing is happening in an asynchronous manner. What I mean here is, suppose there is a limit which is set by your email client that, hey, you should not send more than 50 emails in a second. However, there are more than 50 customers who are placing order in a second. So what is happening here, that payment services is generating more than 50 events and placing them in the queue. Email server is picking them up and sending to this external client API to send an email. But since there is a threshold that not more than 50 emails should be sent in a second, so email server will only pick 50 events in a second to send it. Since there is a hard limit which is set by your external email client that you should not send more than 50 emails in a second, we can configure a threshold on this email server saying that only pick 50 events in a second, so that you do not breach the threshold limit of your external client API. And once the email is sent, that events get discarded. The next 50 events which will be picked on the next second are not getting destroyed, but they are still present in the queue. So this processing is called asynchronous processing. So here SQS can be used to combine 2 microservices together. So whenever there is a queuing system in place which is coupling 2 microservices together, there is a question that how this email server will pick the event. So there are actually 2 mechanisms how this email server can pick the event. There are 2 options. One is push, another is pull. So let's discuss pull mechanism first. So in pull mechanism, the email server will query this SQS queue. Hey, do you have an event for me? Hey, do you have an event for me? At a fixed interval. Now inside pull mechanism also, there are 2 types of pulling. One is short, another one is long. So in short pulling, the email server will query this queue every second. Hey, do you have any event for me? Hey, do you have any event for me? This email server is querying this queue every second. However, in case of long pulling, this email server will only pull event from this queue after a certain interval of time. Let's say 5 seconds or 10 seconds, whatever is configured. So here pulling type depends on the architecture. So if money is not an issue and your event is super important, then it makes sense that you do short pulling because it will consume more resources and ultimately it will jack up your cloud cost. However, long pulling is more pocket friendly, where this email server will query this queue after every fixed interval, pick up an event, send an email, and then again wait for that fixed interval. However, in case of push mechanism, this queue will have to push this event to the email server, and then email server will communicate with an external client to send an email and then discard it. But in case of SQS, it is pull mechanism. So email server will have to pick an event, trigger an email with an external client, and then discard it. So this SQS is not the only way in which we can trigger notifications to the customer. Usually what happens whenever a customer places an order, you want to trigger multiple events like send an email or send a mobile push notification or send a text message. So we have seen this commonly on Amazon.com whenever we try to place an order. As soon as the payment is successful, we get an email that, hey, you placed an order, this is your delivery date and other details. Apart from that, we also get a push notification through our Amazon app that, hey, your order has been placed. So what is happening here, that this payment service is trying to trigger multiple events parallelly. So in order to achieve this, we'll have to create a pub sub model, which is publish and subscribe model in case of Amazon. And to achieve this in AWS, we'll be using a service called SNS, which is Simple Notification Service. Now suppose whenever a payment is done, it will create an event in SNS, and we would like to trigger an email for that event, and also we would like to send a text message to the customer. So now we can see here that whenever a payment service is generating an event, we are triggering multiple events from SNS. So let me explain it again. So what is happening here? The payment service will send a notification to SNS that, hey, a successful payment has been done. Now this email server is listening to this SNS, and this text message is also listening to this SNS. So what will happen that SNS will pick that event, that same event. Email server will also pick that same event. Email server will send that event to email client, and this email client will send an email to the user, and this SMS client will also send a text message to the user. So this means that whenever a payment is done, payment service is creating an event, we are triggering multiple events out of that one event. So this is called pub sub model, publish subscribe model, where there are multiple receivers listening to one event. However, in case of SQS, there is only one receiver who can receive this event, process it, and then discard it. So this pub sub architecture is also known as event driven model or notification architecture. Now there is also a drawback of this event driven architecture, that there is no acknowledgement where the event has been successfully completed or not. What I mean here is that whenever a payment is done, it creates a notification here. Email server is listening, SMS server is listening. Now suppose this SMS server picked up that event and tried to trigger a text message for the user, but somehow there was some problem and the text message could not be sent to user. So in this case, the event is lost, and there is no way we can retrieve that event and put it back into the queue so that after 5 minutes or 6 minutes, that event can be again picked up by this SMS server and a text message can be sent to the user. However, in case of SQS, suppose email server picks up this event to send an email to the customer, and somehow this email client was down and the email to the customer could not be triggered. So in case of SNS, we have a mechanism called dead letter queue. So now what will happen that since this event was not successfully triggered, this event will be put back into the dead letter queue, and email server will try to reprocess this event after 5 minutes or 6 minutes. So in this case, we have a retry mechanism where it guarantees that your event is not lost in case of any error. So far we have discussed that there is no re-entry or acknowledgement in case of SNS. In order to overcome this issue, there is another solution in Amazon which is called FanOut Architecture. Let's imagine we have 3 queues, one for WhatsApp, one for email, and another one for SMS. And each of these queues will have their respective EC2 instances to process the event. In front of these queues, we have SNS. So whenever a payment is done, it creates an event in the SNS. Then that event is automatically inserted in all these 3 queues. Here, there is a possibility that the WhatsApp and the email could be successfully sent to the user, but somehow the SMS was not sent to the user. And here comes the advantage of fan-out architecture, where a failed event can be put back into the queue, because these queues, whatever we have defined here, are nothing but SQS queue. So let me put SQS here. And we have already discussed here for this architecture that SQS is capable of handling retries. Now let's go back to our initial architecture where we saw that users were interacting with the system via load balancer here. What can happen here is that users can overwhelm the system. That is, they can send lot of fake requests, which is also called DDoS or DOS. DDoS stands for Distributed Denial of Service and DOS stands for Denial of Service attacks. So these attacks are done to overwhelm your system. In order to prevent that, we need to implement something called rate limiting on this load balancer. Rate limiting means that the number of requests which can be processed by your system at a given time. For instance, if the rate limit here is 5 per second, and if you try to send more than 5 requests per second, then the server will block you. This is the reason we sometimes see too many requests error. It's not that we can only restrict the users for rate limiting. We can also configure our load balancer to accept all the requests coming from the user, but send requests to the server in a controlled manner. So what will happen? The load balancer will accept requests from the user and it will only forward 5 requests to the server at a given time. This will prevent your server from overloading. Some examples of rate limiting are leaky bucket, sliding window. So let's go and Google and try to search about it. We can see here that rate limiting strategies control the traffic flow to protect system primarily using algorithms like token bucket, leaky bucket, fixed window, sliding window. Rate limiting is a very important concept. Otherwise, for an e-commerce website like Amazon, people will definitely try to exploit it. Now, whenever you have so many requests coming from the server, these servers will try to query the database to fetch data. So let me make database here. Here there is a problem. Suppose everyone is trying to access the database at the same time. This can overwhelm this database. So what's the solution here? In order to prevent this failure, we will be creating multiple read replicas. You can see here that I have not created any write replicas. And that is because if there are multiple writers to the database, the data will be inconsistent. Suppose this server writes to one database, this server writes to this database, then what will happen? The data will become inconsistent across these two servers. And when someone tries to read data from this database will not know which data to pull. However, if there is only one master database where every server is writing, these read replicas can pull from one database and update their databases. Now, there is one small problem here that suppose this server wrote the data to MasterDB and the second server is trying to read the data from a read replica at the same time, then there is a very high chance that this read replica has not pulled the latest data from the MasterDB, and person who is trying to fetch the data from server 2 might get an old data from this read replica. However, replication happens very quickly. So within couple of seconds, all the read replicas will be able to update their database from the master database. Now there is one more concept called caching. So suppose you are doing some complex calculation. So it is always advisable that you cache the data into this cache. Suppose you are trying to fetch a data from the cache and it does not have the updated data. So what it will do, it will go to the MasterDB, try fetching the data, and then sending it to the user. This concept is called cache invalidation, where cache checks whether its data is updated or not from the MasterDB on a regular interval. Now let's further optimize this architecture. What we can do here, we can put a CDN in front of this load balancer. So let me get rid of these users. By the way, CDN stands for Content Delivery Network. The user of this app, which is Amazon.com, is spread across the world. Some are in North America, some are in Europe, some are in India. So in case of CDN, there are multiple machines deployed across the world. And in case of Amazon, that machine is called CloudFront. So here I have added one CloudFront. Let's create multiple copies of it, which is deployed across multiple regions. So let's say this CloudFront is deployed in USA, this is somewhere in Europe, this is in India, this is Africa, this is Australia. Deploying CloudFront will take some time to deploy because it deploys machine in all the regions. Now, since we have deployed so many CloudFront across the globe, these CloudFront internally route the traffic to this load balancer. So all these CloudFront will route the traffic to this load balancer, which is 10.2.3.1. There are multiple users in USA. Similarly, there are multiple users in Europe. Similarly, there are multiple users in India, in Africa, and in Australia. All these users, what we see here, are sending the request to their nearest CloudFront. Here you might be wondering that these CloudFront are machines which are having different IP addresses. Then how the requests are getting routed? This is where a concept called Anycast comes into picture. With Anycast, we can assign a single IP to all these CloudFront machines, and your request will be routed to the nearest CloudFront from your location. Once the request comes to CloudFront, the CloudFront will forward the request to the load balancer. So these CloudFronts are having same IP address. Now suppose a person who is sitting in London in Europe region wants to download a file which contains a list of top 100 rich people in the world. What will happen here? The request from the user will go to its nearest CloudFront and will check whether that file of top 100 rich people in the world is available in this CloudFront or not. If that file is not available, the request will be forwarded to the load balancer. The load balancer will forward the request to one of these servers here, and one of these servers will go to the database, fetch the data, and return the file to this CloudFront here. Now this file is available here, which contains a list of top 100 rich people in the world. And once the file is available here, this file is handed over to the user. Now let's say someone else from the Europe region tries to access the same file. Now in this case, this file is already available in the CloudFront. So what will happen? The request will pull the data from the CloudFront and will be given to the customer instead of querying the database here. So because of caching, what happened here is, first, user request was completed very fast because we saved a lot of latency, because there is a possibility that this load balancer might not be deployed in Europe. It could be somewhere in US or any other region. Secondly, we saved a call to the server, hence saving some compute resources. Since this file was cached earlier, we were able to cancel all the requests to fetch this file for top 100 people in the world going to the server from Europe region. So this is how CloudFront works to make your architecture more robust and efficient. Well, from a beginner's perspective, this is how you design a scalable architecture containing all the basic components. If you have understood all the components we discussed in this video, then congratulations. You can design a scalable, efficient, and a robust system. I hope this video was able to provide you the knowledge of how system design works in a real world. What are the different components and how we can use these components to create a robust and efficient system. If you expect some more videos like this, or do you have any ideas, do let me know in the comments. Until next time, till then, keep learning.